We are the Caterpillar Large Tractor Ladder Latch Design Group. Let's meet the team really quickly going from left to right. We have Dominic Jelenkovic, Blake Rosen, Harsh Bansal, Matthew Villanueva, Casey Spradling, and Albert Rubalcava. So what's the problem the team is faced with? Caterpillar would like a latch mechanism redesign to reliably retain the boarding safety ladder on all their large track type tractors. When the current system was deployed in the field, operators found that the latch failed to stow the ladder on the side of tractors at low operating hours. Through thorough root cause analysis, it was found that there were internal issues with the linear actuator, controller for the linear actuator, and pin misalignment. For customers, this means downtime of the machine and loss of production. And for Caterpillar, this means a sense of unreliability towards their products and a loss of profit through warranty replacements. The goal of this project is to improve the reliability of the mechanical latching mechanism and ensure backwards compatibility while meeting structural and durability requirements. This video will show how we justify and verify our stitch design solution through agile simulation and modeling techniques, followed by testing to verify all of our system requirements. Let's briefly go over how the system works, as this was key to our electrical integration strategy. There are two jobs for this system. One is to extend the pins through bored holes in the ladder, and the other is to retract them. For extension, the operator holds down one of two switches located on the tractor. The rotational actuator engages and swings the ladder up to the latching mechanism. Once the ladder is in position, the proximity sensor signals the rotational actuator to stop and the motor to engage. The motor turns a series of simple linkages to extend the pins through bored ladder holes. The limit switch controls distance of the pin extension and relays to the motor to stop once they have reached the proper stroke length. For retraction, the operator holds down the switch on the tractor and the motor engages in the opposite direction, turning the linkages and retracting the pins. Once again, the limit switch controls distance of the pin retraction and relays to the motor to stop and signals the rotational actuator to begin, rotating the ladder down to the ground.
Here we have our verification matrix, which splits our system requirements into 4 categories and denotes when each test, demonstration, analysis, or inspection will be completed, in either minimum viable product 1, MVP 2, or in the final prototype. Our first set of requirements involves reliability to ensure the mechanism works given our number of cycles and hours for ladder operation. That has to do with alignment, stress, motion, and frequencies. Our second set involves environmental requirements to ensure our system will work in normal mining operations that include a variety of weather conditions. Our third set deals with the mechanical side of the mechanism to ensure durability of the structure, which includes motion, alignment, and forces. Our last set includes design requirements to ensure backwards compatibility, operator safety, and maintenance accessibility.
So this is our Pew matrix. As you can see, each of our designs was evaluated based on its environmental abilities, its durabilities, its cost neutral or less than the current system, its accuracy, reliability, and serviceability. And then as you can also see, higher is better, and the stitch design came out on top. This is the 5th wheel hitch design. It's actually the design that we were running with during PDR, but after PDR, we discussed with our sponsors and it was determined that it was too complex and just way too complicated to be a viable solution. Another design concept was the magnet. The idea was to use the tapered sections and electromagnets to latch the ladder onto the side of the tractor, but it was determined that any debris coming from the mine or anywhere else entering the female tapered section would cause the system to fail, so this design was not selected. One other design concept that was discussed is called the stud. It basically works just like a BNC connector on an oscilloscope works, but it had the same issues as the magnet where any debris inside the system would cause it to fail, and it ended up being too complicated, needing 2 different rotating sections on the ladder. This is the final design concept called the stitch. It's the design that we decided to run with. Basically, it's very similar to the existing design. We took the best parts of the existing design and then we got rid of the problem areas such as the linear actuator. So we're using a motor to rotate the system to extend and retract the pins. This is a diagram of the current design. As you can see, the stitch and the current design are very similar. However, we've removed the linear actuator and replaced it with a gear motor, which will be more reliable. And we've also made the system symmetrical so that there's even force on each of the pins when they're extending and retracting.
This is our system block diagram for a ladder latch system. As based on the diagram, the team design scope is based inside the square dotted boundary. The yellow highlighted items will be interacting with our system, those being the ladder assembly, operator switch, and ladder's actuator. The base plate will be securing the electronics and mechanics mounting, which will hold all the mechanical and electrical components of the system. When the ladder is in operation, the limit switches and proximity sensor communicate to the rotational actuator and the motor through a relay system to control pin retraction, extension, and ladder movement.
The new design consists of three major sub-assemblies: the mechanical assembly, the mounting assembly, and the electrical assembly. One major goal of the design was to maintain the simplicity of the mechanical assembly. To do so, the new assembly consists of both existing parts and newly designed parts. This allows for simple integration and allows the team to achieve our goal. One of the key changes from the current design to the new design is going from an actuator-driven mechanism to a motor-driven one. This major change governed the initial design of the mechanism components, because instead of dealing with the linear force output of the actuator, the system must endure rotary forces. To ensure that the components can withstand real-world loads and stresses, the team turned to the Creo-simulated environment and finite element analysis to iterate the design over 80 times in order to reach a verified design before manufacturing. The mounting subassembly has two major components: the existing latch group mounting structure and the motor mounting structure. Because the new design is being driven by a motor, a new mounting scheme was designed to keep the motor rigid for the duration of the tractor's operation. The motor mounting utilized the existing latch group structure to integrate into the system. Real-world loads that the components would experience during its operation were applied to mitigate risks. Modifications were made to the design based on the results to ensure that the components would withstand the loads without failing. This iterative process continued until the results for the components showed that they were robust enough to handle the loads.
For our electrical integration, we designed a circuit that interfaces with the existing wiring harness on the latch group. Basically how it works is there's a limit switch and a relay for each direction of pin travel, so that when the limit switch is pressed, the relay is moved from the normally closed position to the open position, cutting power to the motor and restricting our pin travel to the necessary dimensions.
As part of our final testing, we took our prototype to the Tucson Proving Ground facility of Caterpillar, where we mounted our prototype on the compatible tractor. Using various tests and specifically speaking accelerated testing, we made sure that all of the requirements of our client were met with the design that we have.
Through an iterative simulation and analysis process followed by testing, we saw the system has overall reduction in stress, higher natural frequencies, adjustability for alignment, and structural and electrical compatibility. Our team has demonstrated that we have performed the necessary system and subsystem analyses to develop our design concept and verify that our design improves the reliability and durability of the mechanical latching mechanism while meeting all Caterpillar requirements.